Today, we are breaking down the Arcee Trinity Large technical report by Arcee AI, Prime Intellect, and Etology AI. This is a big one. We are talking about the Trinity family of Sparse Mixture-of-Experts models.
Right, and the flagship here is Trinity Large, which has a staggering 400 billion total parameters.
But the hook, especially for the engineers out there, is that it only activates 13 billion parameters per token.
It is an absolute beast for inference efficiency.
And the technical details are just fascinating. They swapped out the standard Atom W for the Muon Optimizer on the hidden layers to boost sample efficiency.
Yeah, plus they used a 3-to-1 ratio of interleaved local and global attention, along with gated attention for stability.
Not to mention the data. It was trained on 17 trillion tokens, including 8 trillion synthetic tokens that were generated to be highly educational.
And we absolutely have to talk about the training stability war. They introduced something called SMEU, Soft Clamp Momentum Expert Bias Updates, to basically save the model from a mid-training collapse.
It's essentially a manual on how to rescue a massive run, and the result is a model that achieves performance competitive with GLM 4.5 base, but with the throughput of a much smaller model.
It is a really serious piece of engineering.
All right, let's get into the details. Welcome to AI Paper Podcasts. We are doing a deep dive into this technical report today, and I want you to picture a bodybuilder, just absolute massive, 400 pounds of muscle.
Okay.
But when he goes to lift a car, he's only using his pinky finger, and somehow he is still lifting the car.
That is a very specific image, but I think it actually works perfectly for this.
It's really the only way I can wrap my head around the scale we're dealing with here. Because 400 billion parameters, that is like a ghost town where only a few lights are on at a time, just 13 billion of them.
Right, and that's the core paradox of Sparse Mixture-of-Experts, or MoE models. You want the capacity of a giant brain, all that stored knowledge sitting in those 400 billion parameters, but you want the speed of a sprinter. So by only activating 13 billion parameters per token, they are claiming they've built a model that has the smarts of a giant, but the inference latency of a lightweight.
And it is not just the sheer size. I mean, the engineering under the hood here is wild. They are ditching standard optimizers, they're rewriting how the model does basic math tokenization, and honestly, the training log reads like a disaster movie.
Oh yeah, they almost lost the whole thing.
They really did.
It's so rare to see a technical report be this honest. Usually companies just publish a paper saying, we traded, it was perfect, here are the weights. But these guys admit they were staring at a crash model and had to perform open heart surgery to save it.
We are definitely going to get into that drama, specifically that SMU thing I mentioned, which sounds like a cartoon character, but actually saved millions of dollars in compute.
Definitely.
But let's start with their actual strategy, because they didn't just wake up on day one and decide to train a 400 billion parameter model.
No, and honestly, this is lesson one for anyone listening who works in ML infrastructure. They built what they call a scaling ladder. You do not just push the button on a massive run.
Right, the risk is too high.
Exactly. So they release 3 distinct sizes. First, Trinity Nano, which is 6 billion parameters total. Then Trinity Mini at 26 billion. And finally, the Trinity Large.
So the Nano and Mini, those weren't just smaller products they built for the sake of having a budget option.
Precisely. There were validation steps. When you were about to burn millions of dollars in compute on a 400 billion parameter model, you really don't want to find a bug in your data pipeline or your architecture halfway through.
That makes total sense.
They used Nano and Mini to stress test everything. The Muon Optimizer, the new attention patterns, the tokenization. If it broke on Nano, it was a relatively cheap fix. But if it broke on Large, it's a financial catastrophe.
So let's get under the hood of that architecture they were testing. You mentioned this interleaved attention earlier. They're doing a 3-to-1 ratio, 3 layers of local attention followed by 1 layer of global attention. Why mix them up like that? Why not just use global attention everywhere like a normal standard transformer?
Well, it comes down to the needle in the haystack problem versus raw processing speed. Global attention, where every single token looks at every other token in the sequence, is extremely expensive. The compute cost grows quadratically.
Right. The longer the context, the slower it gets.
Exactly. But local attention, and specifically they use sliding window attention here, only looks at its immediate neighbors. It is incredibly cheap and fast.
But if you only ever look at your neighbors, you lose the big picture, right? And you would forget the context from the very start of a long document.
Which is exactly why they compromise. They do 3 layers of local attention, which handles the immediate syntax and local context super efficiently. And then every 4th layer is a global layer.
Got it.
and they use no PE for that, which stands for no positional embeddings. This global layer basically acts like a synchronization point, allowing information to propagate across the entire sequence.
So you are getting the speed of local attention for 75% of the layers and the long-range context of global attention for the remaining 25%.
Correct, and it turns out this is incredibly efficient for long sequences. It also severely helps with context extension later on in the pipeline, which we will touch on. But there is another architectural nugget in here that I just love, and that's gated attention.
Now, gating usually means adding some kind of mechanism to control what flows through, right? Like a valve.
Yes, exactly like a valve. They apply an element-wise gating to the attention output. They project the input to a gate value, run it through a sigmoid function, and then multiply it by the attention output.
But why add that extra math? Why add that complexity?
Stability. One of the absolute biggest issues in training these massive transformers is what we call attention sinks, or just massive loss spikes, where the model gets overwhelmed by a surge of signal.
Oh, I see.
Gated attention dampens that noise. It prevents the loss from spiking wildly by allowing the model to essentially turn down the volume on attention heads that just aren't contributing useful information at that exact moment.
It's like putting noise-canceling headphones on the neural network.
It's a great way to look at it.
Now, this is a mixture-of-experts model, so we have to talk about the experts themselves. And they made a really distinct choice for the large model compared to the smaller Nano and Mini ones.
They did. For Nano and Mini, they went with fine-grained experts. This is very similar to the DeepSeek V3 style. They had 128 experts and activated 8 of them per token.
Okay.
But for Trinity Large, they completely switched to coarser experts. They still have 256 routed experts, but they only activate 4.
Why use fewer active experts for the biggest model? You'd think more experts means more brain power.
It's all about throughput. When you have to route data to 8 different experts that might effectively be living on different GPUs or different memory blocks across a cluster, there is a massive communication overhead.
Right, the network becomes the bottleneck.
Exactly. By making the experts physically larger and only selecting the top 4, they drastically reduce that communication cost. It is a calculated trade-off. You get slightly less granular specialization, but you get significantly faster inference speed.
And they use sigmoid routing instead of softmax for this, right?
Yes, and that is a crucial detail. Softmax forces the probabilities of all the experts to sum up to exactly 1. So if all the experts are actually bad for a specific token, softmax still forces the model to pick one and assign it a high confidence score.
It forces a choice even if it's a bad one.
Right. But sigmoid routing scores each expert entirely independently. It allows for a none of the above or an all of the above kind of nuance, and then they normalize those scores before gating. It just tends to be much, much more stable for MoE training at this scale.
Stability really seems to be the overarching theme here. Speaking of which, they also mentioned depth-scaled sandwich norm, which I'm getting hungry just saying it, but I assume we can't eat it.
Unfortunately not. It is a normalization technique. In deep networks, the signal can explode or vanish as it travels through 60 or more layers. Sandwich norm normalizes the input and the output of every single module.
And the depth-scaled part.
That means they scale the weights of the normalization based on how deep in the network they currently are. It keeps the signal flow totally consistent, which prevents those massive gradient spikes that cause training runs to literally explode.
Okay, so let's shift gears to the fuel for this massive engine, the data. They built a custom tokenizer with a 200,000 token vocabulary. But there's one specific detail in the report about how they handle digits that I found absolutely brilliant. Place-aligned chunking.
Oh, this is one of those, why didn't we think of this sooner moments in AI?
Sure.
Standard tokenizers, they just chop up numbers arbitrarily based on how often they appear in text.
Right.
So the number 12,345 might be tokenized as the chunk 12 and the chunk 345, purely depending on frequency. This completely destroys the mathematical relationship of place value.
Because the model has to learn that the 12 in that instance represents the thousands place purely by correlation, not by structure.
Exactly. It's making math artificially hard for the model. Trinity's tokenizer forces a split into right-aligned groups of 3. So 12,234,567 becomes the token 1, then the token 234, then the token 567.
Ones, thousands, millions.
Precisely. It actively preserves the human concept of place value. The token 234 in that middle position always represents thousands. This simple, elegant change drastically improves the model's arithmetic performance because the tokenization finally aligns with how math actually works.
That is so smart. Just incredibly elegant. And they also did something specific for languages like Thai and Lao, right?
Yeah, script runs. Those languages don't use white space to separate words like English does. Standard tokenizers often bleed across languages or break characters awkwardly in those scripts, so they explicitly supported script runs to ensure that the tokenizer respects the natural boundaries of those specific writing systems.
Now, they trained this on 17 trillion tokens. That is a lot of reading material. But 8 trillion of those were synthetic?
Yes, almost half the entire data set.
Right.
This was a massive effort driven by tautology AI. They didn't just scrape the web and dump it in, they essentially rebuilt the web. They used a proprietary method called Beyond Web.
Rebuilt the web. How do you rebuild the internet?
Well, in a sense, they took messy, disorganized web documents and systematically rephrased them. They turned convoluted articles into clean Q&A pairs. They rewrote dense text into what they call pedagogical styles. They essentially rewrote parts of the internet to sound like a clear, concise textbook.
So the model isn't learning from angry Reddit arguments, it's learning from a textbook version of those arguments.
Hopefully with less arguing and much more actual reasoning. They also generated huge amounts of synthetic code and STEM data, and they did all this in phases.
Right, the phase training approach.
Phase 1 was general knowledge. Then phase 2 and 3 progressively boosted the ratio of math and code data. The entire idea is to build a solid linguistic foundation first, and then aggressively sharpen the reasoning capabilities later in the run.
Okay, so we have the scaling strategy, the architecture, and the data pipeline. Now we get to the real drama, the training war stories. As you said earlier, this report is surprisingly honest about how close they came to utter failure.
It really is, and I deeply appreciate that transparency from the team. The drama really centers around the optimizer they chose, which is Muon.
Muon sounds like a sci-fi particle weapon. What exactly is it?
It stands for momentum orthogonalized. Standard optimizers like AtomW update the neural network's weights by just looking at the size of the gradient. Muon does something fundamentally different for the massive hidden layers, those big 2D tensors. It orthogonalizes the gradients.
Orthogonalizes? Can we break that down into plain English?
Sure. Think of it as actively cleaning up the direction of the weight update. It ensures that the updates are structurally efficient, which prevents the internal representations of the model from collapsing into a single, useless dimension.
Okay, that makes sense.
It allows for a much larger critical batch size and far better sample efficiency. Basically, the model learns significantly more per training step.
But it's notoriously tricky to tune, right?
Very. They actually had to use a hybrid approach. They used Muon for the internal layers, but stuck with AtomW for the embeddings. And they had to meticulously adjust the learning rates based on fan-in and fan-out dimensions, because Muon behaves so differently than traditional RMS-based optimizers.
Okay, so picture this. They are training Trinity Large, millions of dollars of compute are humming away, everything is going great, and then the crash happens.
The dreaded MaxVO spike. MaxVO measures the maximum violation of load balance among the MoE experts. It's basically asking, are the experts sharing the workload equally?
I'm guessing they weren't.
Suddenly, out of nowhere, the metric just spiked. Total expert collapse.
Meaning the model just decided to route every single token to just a few experts and completely ignore the rest of the network.
Exactly that. And once that happens, the loss curve just plateaus. The model completely stops learning. They were deep into the training run, burning massive compute time by the hour, and the model was just broken.
And they didn't have the time or the budget to just restart from scratch.
No way.
So they applied what they called the 6-step fix all at once. It's like doing open heart surgery while the patient is running a marathon.
It really was. They just threw the kitchen sink at the problem because they had to. But the most important of those 6 fixes was SMEBU, soft clamp momentum expert bias updates.
Let's unpack SME. What was actually wrong with the old way they were updating the bias?
Standard auxiliary-free load balancing uses a sign-based update. If an expert is overworked, you bump its bias down by a fixed, rigid amount. If it's underworked, you bump it up. It is a harsh step function, just +1 or -1. And this causes massive oscillation. The bias just bounces back and forth around the optimal value, but it never actually settles down.
It's like a thermostat in your house that only has 2 settings, freezing and boiling, and it just keeps clicking back and forth between them.
That is a perfect analogy. SCU changes 2 critical things. First, it introduces soft clamping. It uses a tan function. So as you get closer to the target optimal value, the update gets smaller and smaller. It allows the bias to actually settle gracefully at 0.
And the second thing?
Momentum. It remembers the previous updates. This dampens the random noise. If the token load fluctuates just randomly for a few steps, The momentum smooths it out so the model doesn't overreact.
So SVU stopped the violent oscillation. What were the other 5 things they threw at the wall?
They added a Z-loss to control logic growth, because Muon tends to make logics grow huge, which causes its own instability. They reintroduced a small sequence-wise auxiliary loss just to gently nudge the routing within individual sequences.
Right.
They disabled a specific low-precision format called MXFP8, falling back to the safer BF16 for stability. They doubled the initial dense layers from 3 to 6 to stabilize the raw signal entering the MoE layers. And finally, they implemented intra-document masking.
Intra-document masking, which means what exactly?
It physically prevents the model from attending across completely unrelated documents that just happen to be packed into the same training batch. It drastically reduces background noise. So they applied all 6 of these massive fixes simultaneously. And miraculously, the max VO stabilized, the expert collapse rehearsed, and the loss started dropping again.
That is a legendary debug session right there. But they weren't even out of the woods yet. They also had to solve a completely different problem called batch heterogeneity.
Yes, and this is a subtle but absolute killer of a problem when you are training coding models. To be efficient, you pack multiple different documents into a single sequence. But sometimes, purely by chance, you get a batch that is full of incredibly dense, difficult Python code.
Okay.
And then the very next batch is full of super easy web text.
So the difficulty level just spikes up and down wildly between batches.
Exactly. The loss fluctuates wildly. One step is a breeze, the next step is nearly impossible. This thoroughly confuses the optimizer.
And their solution to this was the RSDB, the Random Sequential Document Buffer.
Yes. Normally, pipelines just tokenize and pack documents on the fly as they come in. The RSDB completely decouples this process. It loads thousands of documents into a massive buffer first. Then, when it needs to pack a batch, it randomly samples indices from across that entire buffer to build the sequence.
So it's like thoroughly shuffling the deck of cards before you deal the hands, rather than just dealing them in the exact order they came out of the factory box.
Exactly. It statistically ensures that every single batch has a relatively similar mix of easy text and hard code. And the result was undeniable. Their batch heterogeneity metric dropped by over 4 times.
That's huge.
The loss curve smoothed out almost instantly. It is a relatively simple engineering fix with a massive impact on overall run stability.
So let's talk about what happens after the training. They finished churning through the 17 trillion tokens. Now they need to extend the context window. They took it from 8K all the way to 256K.
And here is where that 3-to-1 local to global attention strategy we talked about really pays off. When they did the context extension phase, they only trained the global attention layers. They left the local layers completely untouched.
Wait, they just didn't touch 75% of the attention layers during context extension.
Correct. Because local attention is only ever looking at its immediate neighbors, it literally doesn't care how long the total document is. 8K or 256K, its job is exactly the same. Only the global layers, the no PE layers, actually need to learn how to handle that massive 256K span.
That must have saved a ridiculous amount of compute.
A huge amount.
Yeah, did it actually work?
Brilliantly. Trinity Large scored a 0.994 on the needle in a haystack test at 256K context. But here's the crazy part. They tested it at 512K, which is double what they actually trained it for, and it still scored a 0.976.
It generalized to lengths it had literally never seen.
Without any explicit training at that length. It's wild.
That is seriously impressive. Finally, they did some post-training SFT and RL.
Yeah, and they kept it highly efficient there too. For supervised fine-tuning, they used cut cross-entropy to save memory. And for reinforcement learning, they used the Prime RL framework.
How do they handle the rewards for that?
They used a mix. They used verifiable rewards for things like math and code, where there's a strict objective right answer. And then they used standard learned reward models for more open-ended creative writing prompts.
So bringing this all home, how does Trinity Large actually perform out in the wild?
It is incredibly strong. In the standard benchmarks, Trinity Large Base is actively trading blows with GLM 4.5 base. It has a coding score on MBPP Plus of 88.62, which is absolutely top tier for open weights right now.
And the speed.
Yeah.
Because that was the whole point of the sparsity.
That is the ultimate selling point here. Because of that extreme sparsity, having only 13 billion active parameters out of 400 billion, it easily beats DeepSeek v3 and GLM 4.7 on output throughput. If you are running this model in a production environment, that throughput translates directly to a significantly lower cost per token.
You know, reading through this, This report really feels like a turning point for how the industry thinks about training these massive beasts. It's no longer just, add more data and hit run. It's fix the optimizer, fix the routing, carefully manage the buffer.
It really raises a provocative question for the whole industry.
Yeah.
We have been relying on AtomW as the default for a decade now, but this paper clearly shows that for extreme sparse MoE models, standard optimization just isn't stable enough.
Right.
The sheer success of Muon here, combined with the absolute necessity of SMEBU and those bounded, smoothed updates, it really suggests that we might be entering the era of topology-aware optimizers.
So are we actually seeing the death of AtomW for these massive scale runs?
Honestly, if you want to push to 1 trillion parameters with this kind of extreme sparsity, I think the answer might be yes. Standard methods just can't handle the load balancing without collapsing.
Well, a huge thank you to the teams at Arcee, Prime Intellect, and Datology AI for publishing such a transparent, honest report. It is an absolute goldmine for the community.
Absolutely. Even just the war stories section alone is worth the read for any engineer.
Be sure to check the show notes for a link to the paper. You are definitely going to want to see those loss curves and the max VO charts for yourself. Thanks for listening to this deep dive into Trinity.
Catch you next time.